are so poor, all they have is money. These sayings are like pretty cool, man. I like dig that. Sometimes they're funny as all get out of town. You know, the tea bags, and the tea bags have all kind of different sayings on them. So that's pretty neat. And I think that's true. Some people are so poor, all they have is money. You know, so I think money's pretty good to have, but you know, you don't have to have it to have fun or to enjoy things, right? So, you know, but it makes life a hell of a lot easier. That's for sure. But actually, just to you know, to be an engineer or something's pretty nice, and then you get money on top. That's crazy. So that's like a buy one get one free kind of stuff. So, you know, you have the satisfaction of being a good person. You know, helping other people, whatever engineering work you do. You might make like drugs for medicine or prosthetic devices, or you might make sensors for cars or something, or cell phones or whatever, and that helps people out. You know, so it's a good field to be in. You know, and that's a sense of satisfaction. That's beyond the money. So that's a pretty cool. Like that's my. I didn't cherry pick that. That's just the tea bag that I picked to make my red tea for my break here. So that's a good little propaganda for you. But that's certainly true. You know, being a starting out in engineering, it's so difficult because everything you don't know what you're doing. You know, and the math is so foreboding, and the chemistry, and learning all these things about pressure and physics and whatnot. And then later on, as an engineer, you're like, those things are really useful. But it's difficult to get the tools at first. So it's challenging to be an engineer. Then all of a sudden, you're an engineer after you start doing projects. So I'm glad you guys are doing this summer activity, because you get to see things, and when you see them, it's easier to study for physics tests and study for calculus tests and stuff like that, because then you get to appreciate that those are tools that help you get your work done, and you have insight that other people don't have, the insight of an engineer. So it's worth it. So your efforts, they're very difficult, but there's a lot of reward in it. So hopefully you enjoy being an engineer. So anyhow, let's get back to my PowerPoint here. Let me put it in this full mode spectrum, right? So we're going to start back in it, and where we're at is, we're certainly more than half finished, because it took me a long time just to give you the overview or review of what's going on. And now we're just in the details of each step. And so the step that we're on now is the primer technology. And we recall from our initial discussion, or the overview discussion, that the primer was like, we know that the substrate usually has, a lot of them, especially dielectrics, are going to have, because they have a lot of dangling bonds, they're going to have a lot of, and water's polar, right? So all these engineering things or physics things or chemistry things come into play, and they're going to be wet. You can't see they're wet, but we're going to try to put this organic polymer on the top, and we really can't do that. So what we're going to do is, to our wafer, we're going to make sure that we have strong adhesion. And just from like regular English, primer. So the used most of the time is called hexamethyl disazoline, or I can't say it right, and hardly anybody can. So we call it HMDS. So nobody says this, I don't think, unless they're really good with their linguistics. But most of the time, everybody just calls it HMDS. So more power to you if you can pronounce that word. I would have a hard time doing it. And this is our primer. And basically what this primer does, this chemically promotes the adhesion of the photoresist by displacing any water left behind on the substrate surface after the dehydration bake, and reduces the surface tension. And the surface tension is the energy on the surface. And I think throughout the summer here, or things that you should look at in engineering, is a study of surface tension, or the intrinsic bonds on the surface, and those things like wetting angle. They're really, really important for a lot of reasons in deposition and lithography and bioreactivity. So that's something that you should pay attention to later in your studies here. So the HMDS actually primes the surface by adding an organic layer of hydrocarbons. So this starts our bond. Does that make sense? So it's a two-step process. And basically what it's going to do is, it gets rid of the hydroxyl groups, which is like the water stuff. It displaces them. So it's kind of like dry gas in a car. And what it's going to do is it'll start that bond by applying these C's and H's. Does everybody see that? So it does two things. What it does is displaces the water and then starts that process. So that's the definition of the primer. So intermittently, I'm going to drink my tea. I hope it's not like big gulps or something. Hope that doesn't sound crazy. I love my tea in the morning. So HMDS, there's different ways that we can apply it. So now we know what the HMDS does for us. And specifically, once we understand that, now we want to divide that concept again. And when we divide the concept, what we're going to say with this concept is there's probably, well, there's a multitude of ways of doing it. But the three of the most popular ways of doing it are called immersion priming, spin priming, and vapor priming. And what would we say about this as engineers? They probably all have a place where they're really good and an application where they're not so good. So as engineers, what we would do is decide which one was best for our application. Does that make sense? So that's why there's 3 or 5 or 10 different ways of doing it. As engineers, we're value decision makers. And what we do is we fit the best application to our product. Does everybody see that? So let's take a look at these different types. So immersion priming is the easiest method. And basically what we do is we just take our wafer and we dip it into a bucket of our HMDS. And what the problem with that is, well, it's wasteful, right? And then the wafer itself, according to Murphy's Law, is probably going to have dirt on it or dirt on the back of it, right? Dust or contamination. And now that's going to go in my HMDS. And where is that dust or dirt going to wind up? Well, you know, it's going to wind up on your wafer where you don't want it to be. So this has, you know, this one down at the bottom, it exposes the substrates to contamination. And the contamination would be, per se, random dust or particulates, whatever you want to call it, on your wafer. And now that's going to be trapped in your fluid. And you know, if you ever do something, it's going to work out that it's going to be, that particle is going to be plated back on your wafer in exactly the wrong place, right? Because that's just life deals you those cards all the time, right? That's called Murphy's Law. So we don't want to have that. So immersion priming is kind of good because it's simple. I mean, the whole concept is get your wafer with the tweezers, dunk it in a bucket, right? But then look at that too. Why would it be bad? Well, now we got a bucket of contaminated HMDS, and what do we have to do with that? Well, we got to dispose of that. And anytime there's disposal, it's kind of like it's a load or whatever you want to call it on the environment. Does everybody see that? And then I really want you to know this and say this in an interview, and you'll probably get a job. When you buy material, it costs a certain amount of money, but when you get rid of the same material, it probably costs you more. That's what people care about in manufacturing. Does everybody see that? So when you buy a gallon of HMDS, it costs a lot of money, but probably to get rid of it, safety with EPA regulations, et cetera, which are good regulations, it probably costs you a lot of money. So immersion priming is bad for that. Does that make sense? What we could do is we can upgrade this process to spin priming. So we put my wafer on a chuck or your chuck, and then we just put a couple drops of that fluid, the HMDS on there, then we hit the button and we spin it just like the photoresist, and it coats the wafer. And what this does is allows us, for on average, to use less resist. And then we don't have contamination from the back of the wafer. Does everybody see that? So it's an extra step, and now we need a spinner. And a spinner probably costs about 15 grand. But, you know, that's okay because it's an upgrade from the immersion. And then we could also have spin priming, which is a little bit of an upgrade from just putting it on bulk. What we could do is we can move the primer dispenser and then spin at the same time, and we use less fluid. Does everybody see the drops coming off the edge? So this is a excuse me, a better way of doing it. So this is the spinner chuck and how we would, you know, spin a wafer on there. So we place our wafer on the chuck. There's a slight vacuum on there to hold it in contact so it doesn't fall off, and then we rotate it at high speed. And we generally would use the same method with both the HMDS, and then later after that's dried, we'll put the photoresist on the same method. Often they incorporate these, they integrate these processes on like a robotic assembly line. Does everybody get that? So that's what we have to know. And then we could also do this in another way. We don't have to do it in a liquid form. We could do it in a vapor form. So we would put this in like an oven that kind of looks like a microwave, and then it's heated up, and then we have a bubbler in there, and we bubble this vapor, like the steam of the HMDS, and then that lands on the wafer, dries out the wafer, and builds up a steady state film that it doesn't get any thicker, and we could leave the wafers in there for 2 weeks. And they're just in there in some like suspended animation thing to where they're like dry and have that coating on there, and they're just built up. They often call those ovens YES ovens, Y-E-S, like the affirmative, yes. And it stands for Yield Enhancement System. Again, that's like Hershey bar, you know, like Hershey PA or Hershey Company for a chocolate bar. They would say YES ovens, and they could be any brand, but they're the brand that makes them, like Crescent Wrenches or Kleenexes or Kellogg's Corn Flakes or whatever. So they would call these ovens YES ovens because they're the brand that's most popular in applying that. So this is what it looks like. We would have a gas inlet, maybe of like nitrogen or so. We put it through a bubbler, which would be like a sponge maybe, and then it would foam up this stuff, and then the water, that vapor would go into this oven, and the ovens are heated up, and that would pass that vapor through there, and that would coat the wafers, and we could leave them in there for an extended amount of time. Because after a while, a day or two or so, that HMDS actually evaporates off the wafer. So if we had an assembly line and a machine broke down, how could we keep these wafers and not like throw them away or redo it? We would actually just put them in a YES oven, and they would stay in there until we need to do other processes with them, you know. So that's helpful to understand. And then how would we apply the resist? Well, we saw that before, very similar to the HMDS, but we'll take a look at that. There's the static spin, the dynamic dispense, and then the moving arm dispense, and then automatic spinners. And that's the integrated system. And we discussed that a minute ago, but I wanted to review that again. So the static spin, the substrate's placed on a vacuum chuck, and then we put a lot of drops on the middle, and then we spin it. And then the problem with that is we get a lot of debris that comes off the wafer. So like when you go into your labs, they'll probably coat those spinner bowls with aluminum foil, and then we put a lot of that resist on there. Then we hit the button, and a lot of that resist coats on the wafer, but it also goes on the aluminum foil. Does that make sense? I would say the majority of the resist is contamination that we have to throw away, and resist cost $4, $5, $1,000 a quart. So I mean, $400 or $500 a quart. It might cost $800 a quart. It might cost $2,000 a quart, depending on. Makes sense. I mean, thousands of dollars a quart. So the static spin is probably not good if you're in manufacturing and doing a lot of wafers and your resist is really, really expensive. We use the Shipley 1800 series resist, 1805, 1813, 1827, and I'm sure you're going to see that at your schools. And that's because that resist is rather inexpensive. Does that make sense? And it'll be hundreds of dollars a quart. That's still expensive. But the thing about the resist for our demonstrations and for lectures and for school, we probably have to throw it away before we use it all, because we don't use a lot, probably use half of it, and it lasts a year or two, and then it goes bad, kind of like mayonnaise, because it's an organic polymer. Does everybody see that? So things go bad in your refrigerator, right? So after a while, you have salad dressing or mayonnaise in there. If you leave it in there for a long time, it's going to break down, and so the resist does the same thing. So the resist, being an organic polymer, it'll break down after a while. So we use 1813 because it's rather inexpensive, or 1805, and then we usually throw most of it away. So the static spin for us at the university isn't that bad, because we probably buy more than enough, because we don't use that much. We wouldn't have that problem in production because we're continuously using it. Does everybody see that? So there's a disconnect to what you would do in a university environment when you train for lithography and what you would do in production. So naturally, our stuff is a demonstration kind of thing. So we use limited amounts of material. In production, it's production. So you use materials, the name of the game, right? So That's an issue you don't really face in production. You're going to use that jar up rather quickly compared to, and they sell it by the quarter, they sell it by the gallon, right? And gallons could be thousands and thousands of dollars depending on the type of resist. So dynamic dispense, this, you can see that with this. We apply the resist, and as we spin the wafer, we apply the resist. And if you think about it in your mind, that's a way that we're going to conserve the amount of resist that we drop on the wafer, because it's going to be more uniform. So we get less like splash that comes off the wafer. Does that make sense? And that's what these techniques are doing, the dynamic dispense and the moving arm dispenser. What they're going to do is we're going to apply less resist. And certainly this would be important in industry because resist is so ridiculously expensive. Does everybody see that? So this is what we do. So we're rotating the wafer when we apply. That way we don't need as much juice, photoresist juice on there. And being that this photoresist is insanely expensive, that this hardware pays for itself, right? So it's cost effective. So we can also have automatic dispenser units, and they're basically like a robot. They're probably as big as the desks that you're sitting at, that you're taking notes on, and it's like a whole assembly line. So we put a cassette of wafers on there, and it does all these things with a robot. And what's good about robots are they're consistent compared to people. So they're going to take in the wafer, apply the HMDS, apply the resist, do the hot bake or the soft bake, do all that kind of stuff, and then prep the wafer and then put it back into the cassette. So this is an automated system, and they're usually waist high, and there's a like polycarbonate glass that you can see through and watch the robot do its work. And the advantage of that is that's all like in a sealed environment, so you don't smell all these things and all those organic polymer kind of stuff. They're contained in there, and you're not putting that in the environment. So it doesn't go into the atmosphere where it gets scrubbed, right, by some kind of mechanism. And it's not, the user doesn't see that. And again, whenever you're dealing with organic polymers, and things that are solvents or whatever, they're really bad for you. Like, so when you pump gasoline into your car, it says right on the gasoline pump, you don't want to inhale this stuff because it's bad for you. Does everybody see that? So these solvents like nail polish remover and stuff, you want to have a fan going when you use them, and you don't want to be smelling that stuff because it's bad for you. Does everybody see that? So this containment unit, that this robotic section is processing these bad smells and this chemistry, they're contained there. It's actually very environmentally conscious to the user and to the general environment. Does everybody see that? So that's why automatic spinners are pretty cool. And then they're robots, so they do things consistently well. So the spin on the resist, there's different factors: the time, the spin speed, the acceleration rate, and certainly the adhesion rate. So those things are something we look at. So the electromagnetic spectrum, this is our energy, like our light energy. So we want to look at that, and where do we see this? We want to identify, again, we're narrowing down these steps and looking at the details of these steps. So let's take a look at that. So here's the electromagnetic spectrum. Radio waves are the longest, right? And then gamma rays, X-rays are real small. So when you get them that they're tighter, there's more energy density in there. Does that make sense? So as you get smaller wavelengths, there's more compact. It's more like a DC kind of thing. There's less on and off time. So there's more energy in there. So these are the wavelengths. If we look at the electromagnetic spectrum, we look at, is there a bigger picture? No, this is a good picture here. But this picture, what's like really cool is, we're interested in these things up here. So this blow up on the top of the picture, if we go from the infrared to the ultraviolet, and we like to, and there's the visible right there. We like to work in the ultraviolet because that gives us smaller feature sizes. And then this is a really good map down below. This shows us that we're making things that are as big as a bacteria, and the ultraviolet gives us that we're making things on the scale of viruses. Does everybody see that? So this is, I must have said the word virus 20 times so far in this presentation, because one of the things that you should learn, certainly if this is your first look academic look at nanotechnology is you really have to have a linkage of scale in your mind. So to understand this light is as big as a virus, and we're making things for Pentium chips as big as a virus, that's brilliant. Does everybody see that? And in some senses, that should be rewarding to you too, because now you could say, hey, I can make things as big as a virus. That's powerful. Does everybody see that? That's like, that's a lot of you know, mind strength right there, that you could do these things for society. So this shows the wavelengths on there. Does everybody see that? And naturally, we want to get into things that are smaller things, like on the right of my chart here. They're going to provide things that are smaller. We worry about things down at that level like X-rays, because the X-rays themselves have so much energy density, they begin to be damaging to things like silicon dioxide, organics, right? And then other things like that. So they tend to be a little bit more troublesome when we get down into X-rays. They get to be prohibitive for other reasons, like our materials, while we're doing our lithography process, and that's what we're trying to do, they might actually pose damage to our substrate. So they tend to be, in some senses, relegated or questionable. Does that make sense? So there are no such things in some senses as X-ray sources for the most part. Again, I'm getting in shady ground here because they are, but we don't use them in production mostly because they tend to have bad qualities that damage our substrate. So we like to play with ultraviolet light the most because it doesn't damage things that much. Does everybody see that? We all know ultraviolet light's bad for us and would give us things like, per se, skin cancer. So we have to be cautious about that. So these are the spectrums that we worry about. So we like to work in between 480 and 4 nanometers. Does everybody see that? And that's going to give us the resolution of our feature sizes. Does everybody see? And 4 nanometers is crazy small. We usually like to work in, I guess, electronics, maybe a number like, I mean, I'm just throwing this out there, 1/10 of a micron, maybe less than that, you know, something like that, you know, around in that area. Below that, certainly, but not that much. When you get down to 4 nanometers, that's really imposing, you know. So the wavelengths that we would use in contact, because that's today's discussion, is the things that are reminiscent of the Carl Zeiss contact aligners. We often would use one of the cheapest light sources that have a high energy in a specific spectrum would be the mercury vapor lamp. And the mercury vapor lamp puts out a few peaks that are very usable. The ones that we like to use the most is the smallest peak that has a moderate amount of energy, a good amount of energy, and that would be the 365 nanometer peak in the spectrum from a mercury vapor lamp. And I put these asterisks there, and I put that note in there. It's desirable because this is going to make the smallest devices using a mercury vapor lamp at the cheapest cost. Does everybody see that? So this is an intersection of these graphs that we get, like what we want and then the cost that we want. Does everybody see that? So that's what we want. So 365 is like the darling, the one that we want the most, you know. And this is a typical emission spectrum. And this is wrong a little bit because I know for 365 is usually 100% right here, and that's what this one is calibrated to, and that's true. That would be like our norm. That's our reference, right? But the 248 that's down here in a mercury lamp, it's not like 30 or 40% like it shows here. It's actually 20%. That's a standard representation of the light intensities, and that's what we would use. So this is, somebody drew this, public domain, from my department. So the TAs, I sketch things out and then I let them draw it in paint or something. So that guy drew this one a little bit wrong. I think it's corrected in the next slide that it show you it's roughly 20. But I do want to say, over time, these magnitudes of these spectrums are going to change. So you can see this when you put a new light bulb in, like a fluorescent light bulb in the kitchen or something. It's really bright for a few days and then it dies down, right? So emission out of lamps usually takes time to reach a per se steady state. and so do lasers, right? They generally take 5 minutes to warm up so that they would reach a certain thing. They take one, they're putting out one, wavelength. In a laser, it's a different ball game. But lamps themselves take a while to per se reach a steady state. And as a lamp gets like 2 weeks old, these spectrum elements are going to change in magnitude. Then it's different when at 2 months old. Does everybody see that? So I want to make this point. When you put a lamp in, you get a spectrum like this, but that spectrum is not consistent. The spectrum changes because the lamp changes and the light that comes out of it changes. So this leads us to, and this is very important so you know this is true, you calibrate machines. You actually put a sensor in and you adjust the power so that you get consistent energy. And that's this energy, see this line right here? Let me go back and get my crazy annotation out, my draw again. So that we're looking at this line right here, the 365 at this energy. So it's that energy multiplied by times. That gives you your dosage. So dosage is this energy peak times like 6 seconds. Does everybody see that? So let's look at this energy peak. Oh, let's say this one here is 50%. It's not, right? And I can't draw a 5. Let me see if I can draw a 5. So this is 50%. I'm making my line crooked, but we're going to say that's around 50%. So if I looked at this, if this one gave me the amount of energy in 6 seconds, because it's 100%, let me draw that line crooked. It's 100% right now. So it's 100%. In 6 seconds, that would give me my time. So this one is 50% of that. Now it would take me 12 seconds to get the same amount of work done. Does everybody see that? I'm trading time times the magnitude of this peak. So before one of the girls there at NSU, she asked that question. She's like one of those things like, what I don't understand dosage. I think that was part of her question, and hopefully I answered it, but I'm reviewing it again maybe to make this point clear. So what we want to do is we want to get a certain amount of work done, and that work done we're going to define as the term dosage. And the dosage is the relative magnitude of the energy multiplied by the dwell time, the time that we apply that energy. Does that make sense to everybody? So in here, my example is this peak right here is 50%. So I'm going to have to double the amount of time to get the same work done as here because this is twice as high. So for example, if this one here was 6 seconds, then I'm going to have to take this peak is going to have to be times 12 seconds to get the same amount of work done. Does everybody see that? So this is the concept of the dosage. So I want to make that point clear. So let me get my crazy eraser out again. Doesn't seem like I've been talking for 2 hours to me. Maybe you guys are saying, oh my God, it seems like he's been there for 2 weeks. So thanks for the compliment. So not much more, guys. So these are the peaks that you get out of mercury vapor lamp, right? But say we want even more energy. Well, that's all you can get out of a lamp because you can put more energy, but the lamp runs out of the ability to emit light, right? So to get around that, if we wanted to even have more energy density, more energy, like a bigger peak, we can go to things called excimer lasers. And what an excimer laser is, we can recognize these as noble gases along with a halide gas, right? Like a group 7 gas, right? So these gases in here, so these combinations, when we put them together, like this xenon fluorine, we're going to get a laser that has a wavelength of 351. Does everybody see? A real popular, are these krypton fluorines, right? 248. And another popular laser argon fluorine is 193. So these are going to be, let me go back, they would be like these peaks, but they would be an individual peak. This represents the light, right? But I'm just showing you a laser can do the same thing. But a laser would do one of these individuals. And we have what we want to do, like on this drawing, we want to go to the left because left is smaller. Does everybody see that? So the mercury vapor lamp in here, if we go to this drawing, this shows us typical mercury vapor lamp. And right here is, this is a mercury vapor lamp. Let me get out my crazy magic markers. So here's my mercury vapor lamp here. So I got to take this amount of energy times time to get my work done. If I were to apply a laser, this krypton fluorine laser, look, I can get this thing to be, I don't know, what's this, 20%? It's going to be 5 times more energy in the laser, which means I can do the same amount of work in 1/5 of the time. Does everybody grasp this? It makes my machine faster. So I'm getting my same amount of work done, but by increasing the energy with a laser, now I can make my machine faster. Then I couple that with the idea that I'm going to finish this on a hot plate with the deep UV resist, which is a different chapter, a different theme in lithography. And now I can make it even faster. Does everybody see that? So now literally what I want to do is make my steppers lightning fast. And why do I do that? So that I can lower the cost of production. Does everybody see these things? So these are technical concepts, physics concepts, chemistry concepts, you know, that we're trying to understand. But the reason that they're important is it's for money and production. Does everybody see that? So, you know, I just want to, let me get this annotate button again, get rid of my eraser. But I want to make this kind of like clear, and I think I do a moderately good job of it. I teach manufacturing, right? So nanotechnology is the area of manufacturing, but I care about the most about things that benefit society in a cost-effective method. And that's a really that's a high performance game. Does everybody see that? That is really good engineering because we got the constraint that we have to do this very, very smart, but also with limited amount of money, as efficient as possible. So I think it's one of the definitions of an engineer is we're efficient people. Does everybody see that? We're really, really efficient people so that we could make resources go further and benefit society, right? So this is what we try to do as engineers. So these concepts are pretty universal. So then the post-exposure bake, after we do the deep UV resist, right, we set up this catalyzed acids in there, and then when we do that, we do the post-exposure bake, and it allows this reaction to take place. So let me go back up in the notes and then refresh your memory in case you're thinking about lunch. I'm getting hungry now. My stomach's growling. So I'm not, maybe you're not paying attention anymore because you're hungry. Me too. I'm hungry. So I'm thinking about what should I eat for lunch. But we're going back to this slide here. Does everybody see? And we're almost done. But we're referring to this slide, and this is what we're doing at the point that I'm discussing right now. I'm just trying to link these things together for you. So what we do is we do this post-exposure bake, and then we're doing that process where we're catalyzing these acids and stuff like that. And then, so what we're doing is we're allowed to reduce the light dosage because we're substituting it with this heat energy. Does everybody see that? So this is mostly, you could do this in a contact system. You know, the contact aligner, our subject for today, but this is always, always, always done in a stepper. Does everybody see that? And this is always all how your cell phone parts are made. So this is always important in a job interview. Does everybody see this? This discussion, I think this is probably one of the more embedded complex discussions that we had today, and why I was allocated a few hours. I had the presentation done in 15 minutes, right at the beginning. I think you had an overview that was sufficient. But the discussion that was embedded in here, I think is the most difficult, was this post-exposure bake and deep UV resist and why we need them. And I'm telling you, we need them or else we wouldn't have steppers and you know, $50 million stepper tools and all that other stuff, and it's a big thing. So you need to understand that. So this is on a DP resist. This slide discussed that, you know, the hot plate itself is very, very critical. And you guys are going to lose faith in me and think that I'm crazy. Maybe you already do, but a really good hot plate is over $10,000. I actually said that correctly. When you have really high performance hot plates, for them to give you the appropriate magnitude of heat energy, it's insane. I mean, I think it's insane that lithography tools can cost $50 million, but something that like heats up your tea like a hot plate being $10,000 or $15,000 is really something. So like here at Penn State, we have advanced lithography and advanced lithography techniques and like e-beam lithography. And the guys that do e-beam lithography, they have separate hot plates, and those hot plates cost that amount of money. In fact, I was the first engineer at the nanofab here at Penn State. This is going back 20 years or more. Oh, 25 years. I'm so old. More than 25 years. I'm getting older. I'm getting more depressed as I tell the story. But one of the first things we did was bought e-beam lithography tool, and it was millions of dollars. And then my mentor at the time, Bob Davis, talk about brilliant people. You know, so Dr. Bob Davis, he's at Ohio State now. So lucky that I had him as a mentor to teach me things, right? So the guy tells me, he's like, hey, go buy some hot plates, buddy. And I'm like, yeah, Bob, I'm in, you know, I'll go do that. And I'm helping out, you know, process this lab. And so I go and I call up the company, and the guy says, you know, a hot plate's like 14 grand. And I'm like, what's wrong with this phone? I'm like, the phone's broken. You said $14,000 for a hot plate. And he's like, yeah. And I was like, get out of town, you know. So I didn't realize. So this is the story to make this slide real, you know, that you need to have these performance hot plates. For most lithography, the ones that you use, when you go into the lab, you can put temperature probes on them, and you'll see that they float up and down 5 degrees. And you could do that with Shipley 1813 resist, and it's okay because that resist isn't like high performance, and our needs aren't that high performance. But when you look at making things as big as a virus for a cell phone, you have to have high performance hot plates. So there's a story for you, and it's kind of a crazy story, right? And those things are true. So you probably can look it up on YouTube or something like that, or ask Carsoon, you know, how expensive are hot plates or the nanofab when you go in and do these things. Like really good, a good hot plate's probably $1,000, but an excellent one is like over 10,000. That's amazing. That's crazy amazing, right? And this is the acid catalyzed reaction. Again, the same story that I told 3 or 4 times, and this is what we're doing. So we're doing a 2-step here. We set up the reaction with the light, and then we finish the reaction with the heat. And that allows us to get more wafers per hour done, right? So that's in manufacturing for semiconductors, what they talk about manufacturing is wafers per hour. Does everybody see that? That tells you how cost effective your production line is or how effective your tools are. And then we do post-exposure bakes, and they do a lot of things. They might get rid of standing waves that are on the side, and the standing wave is a reflection from the bottom of the wafer, and it constructively interferes with the incoming light source. And then you'll actually see in your photoresist, you'll see these lines. So when you go in and look at your lithography, if you have a chance, you can put them in a scanning electron microscope, and you could see this optical interference on your wafer. And we could use other things that I didn't have time to discuss today, and we often don't do in contact lithography. We could do things like anti-reflective coatings. We always do those and that type of technology in stepper technology, but that's for high performance devices. But for contact, we generally don't do anti-reflective coatings. I'm not saying that all the time, but it's rare. Rarer, or it's not standard maybe. I'm thinking of good words to describe it truthfully, right? But in steppers, always is a term, you know, always anti-reflective coatings. So I'll leave that, and I'll leave that for the next presenter when they discuss, or if you have an opportunity to increase your understanding of lithography, to look at stepper technology. But I was trying to do a couple things here today talk about contact and then extend your knowledge into steppers, right? So I was trying to get two birds with one stone, right? And then development. So we do development. And again, this is going to get rid of the weakened photoresist, right? To remove it so that we have a pattern. And we could do the same thing that we did before, the same type of algorithm. We can do immersion or spray development or puddle. And they follow the same theme, you know, so we can do this immersion. Oh, that's for rinsing. So that's a wrong slide. So forget about that one. We can do the develop and then put it in a rinse and then a dry, right? This is the immersion way. So we do that here at Penn State. We actually get like a dish, like a Corning glass dish that we buy at Walmart, right? So we go to Walmart and we buy these. And typically they're in the cooking section where you'd make brownies. You know, it's a good dish for brownies. And we would clean them out. We use this Corningware dish, and that's what we put our developer in. And we also put our water, rinse water, and then we use the rinse water thing. Does everybody see that? So our developer, our immersion system, we would use glass containers that are Pyrex, and we buy them at Walmart. But you could, not the ones we use in a lab, but you can buy them at Walmart and then make brownies in them or something like that. Does everybody see? Got to watch because you can burn your brownies in them. And you always want to put walnuts in your brownies. This is a tip. So chocolate brownies deserve walnuts. So anyhow, spray development here. A substrate's placed on a vacuum chuck, and then we're doing the same thing. We put a spray on there, and then that reduces the amount of developer that you use. Does everybody see that? And then the puddle development, you can put it on the wafer and then spin it off. So we've seen those themes before, and the same themes in HMDS application and in resist application. And then we use those same themes or methods, and we would use that into development. So this is our, you know, the end of the presentation, and, you know, some pictures for us in case you have questions and I can point to them. But this shows us, you know, the global market in lithography, and it keeps on growing. So that's kind of like real nice that we could see that there's jobs in this area. So if you're taking this, you know, summer course, this is the presentation today. I think I'm going to have this, I'll save this recording and put it on Nano for Me. You know, people can watch this at their leisure, you know, as a, like a YouTube kind of thing, that they might want to look at somebody discussing elements of contact lithography. I think I'll publish this on there. You know, I like to share knowledge. I think sharing knowledge is cool. So I'll publish this on Nano for Me, and hopefully, and we can do that. So you guys have any questions here? Penn State guys, or, you know, the guys that are on that next building over? I'm sitting in my office. Or NSU guys, any lithography questions? Everybody's good. I'm going to look at my clock. 11:30, so that's about the time I was told to do, you know, finish around there or leave some time for questions. Any questions, guys? We're all good. We're all good. You guys are going to be good engineers. Let me put that on there. Yes, I hope you are. I hope you enjoy your summer. I think it's really wonderful that you know, you take the time. It's a wise investment in your future. Come and look at these things, and you could look at them hopefully to be excited by them, and then other things, maybe this isn't your cup of tea, and then do something else. And then what you should learn in nanotechnology, or this review, maybe you're never thought about, like, you're like, I want to do nanotechnology, but I really love chemistry. Hey, do them both. You know, do chemical things or organic polymers, and then satisfy this niche, you know, this one area in nanotechnology, which would be lithography. Or maybe you like physics and optics. So, hey, be an optics guy, work in lithography. You know, you like Snell's equation and convolutions and Maxwell's equations and things like that, then hey, lithography's your cup of tea again. You know, hey, you like to do robots? Hey, lithography's your thing. Does everybody see that? The steppers are like insane robots that cost $50 million, you know, and how precision they are is just brilliant. So if you like to do robots and control and electrical engineering, programming, program lithography, program the robots that do lithography and steppers. So embedded in lithography are all the STEM disciplines. So if you happen to have a gift or a knack like organic chemistry, or you like to do electrical engineering, or you like to do programming, you could find a home somewhere within these realms of nanotechnology. So these are things that you should learn in the summer, you know, so you have a wise investment in your time. So do things that you enjoy. You know, if you enjoy optics, do that. Do it in nanotechnology, because, you know, this is money. I'm not being, like I said, on my tea bag. Let me read that again. Some people are so poor, all they have is money. So not just for money, but there has to be a market, right, for your skills. And then you're really appreciated. So that's more than money. So if you're doing something like have a very good understanding and gift for lithography or optics or programming, then take that gift and use it somewhere in nanotechnology. And I'm sure you could find a place in nano manufacturing to use that. And look at this slope on here. You could always have a job and you can always be contributing. So I think that these things are where you want to be. So no questions, guys. How about moderators? You guys want to sign off and say there's no questions, or is everybody good? Then I'm going to end the session because my stomach's growling. I hope you have a nice lunch. I think I'm going to go to lunch with one of my colleagues and discuss engineering, actually. And then I have a car appointment to have my oil changed. All right, NSU guy, what do you want to hear, buddy?
No, nothing. I just want to tell you that we don't have any more questions. We're good.
All right, thank you very much.
Thank you.
All right, well, I'm going to stop my share and sign off. And thank you very much for your attention, and good wishes for the summer, guys. Take care.
Thank you.